everyone, this video will review one sample t-test in preparation for the discussion for two sample t-tests. The one sample t-tests were discussed in chapter 11 of the lab manual and in class last week. First, we'll talk about the methods, and then we'll move into a tiny bit of Excel, and we'll mostly be reviewing how to do a one sample t-test in R. We'll also look at how to do confidence intervals in R. A review of the one sample t-test general methods, which you can do with any number of steps as long as you hit each of these points. These steps are just written out in a way that kind of follow the way you've seen the problems on your assignments and in the study guide, and what you can expect to see on future exams as well. Step one for any statistical test is to figure out what type of test you're doing and to write out the hypotheses for your main test. Step two is to choose your level of significance, that is alpha, which is usually 0.05, and it would be given to you. Next is to find the t-crit values and the t-calc value so you can compare them. Finally, calculate your p-value using R or Excel, and draw statistical and biological conclusions. This slide is a reminder of the hypotheses we use for two-tailed and one-tailed t-tests. These apply to one sample and two sample tests. In this example, we're using a one sample test because we have one sample of data that we're comparing to a single reference mean that has been given to us. A two sample test would have two data sets to compare. For a two-tailed test, remember we only are interested in if there is a difference between the means. So our alternative hypothesis says the mean of our sample data is not equal to, is not the same as the reference mean. The null hypothesis for a two-tailed test would then be that the mean of our data is the same as or equal to the null hypothesis, the null mean, the reference mean. For a one-tailed test to the left, remember it's easier to start with the alternative hypothesis because it matches the direction of the tail. For a left-tailed test, the alternative hypothesis says that the mean of our sample data is less than the reference mean. The null hypothesis should complement that, so it will say that the mean of our sample data is greater than or equal to the reference mean. Remember that the equal sign always goes in the null hypothesis. For a right one-tailed test, remember again to start with the alternative, which says that the mean of our sample data is greater than the reference mean. The complementary null hypothesis is that the mean of our sample data is less than or equal to the reference mean. As a reminder, we can't use R to find the t-critical values, but we have two other options. The first is to use the t-value table with alpha and the degrees of freedom. The second is to use one of the t.inv functions in Excel. For a two-tailed test, you will get two symmetrical t-crit values using the t.inv.2t function with alpha and degrees of freedom. For a left-tailed test, remember that Excel typically calculates to the left, so we just use t.inv. Since the t-distribution is symmetrical, for a right-tailed test, all we need to do is use negative t.inv with alpha and degrees of freedom. This next slide is a reminder that you should always draw out these distributions and plot your t-crit and t-calc values. This will help you easily come to your statistical conclusion. For a two-tailed test, you have two t-crit values, making two regions of rejection. For left-tailed and right-tailed tests, you only have one region of rejection on that tail. Remember, the region of rejection is used when we find the t-calc value. If t-calc is in the region of rejection, that is beyond or more extreme than the t-crit values, this means that we reject the null hypothesis. If it is in between the two t-crit values, or if it is not more extreme than the t-crit values in a one-tailed test, we accept the null hypothesis. The last slide I'll show here discusses p-values, which are found in R, but you can also find them in Excel using the t.dist function, using tcalc and degrees of freedom as your arguments. For two-tailed, we use the .2t. For one-tailed left, we use t.dist, remembering to use this true argument. And for right-tailed, we use .rt. With that said, let's go ahead and move into Excel. Here I have open the template file for chapter 11. This problem was the pH of soil with and without fertilizer. And the question asked if this fertilizer significantly changed the pH. So we're only interested in, is there a difference between the pH of the soil measured with fertilizer and the known pH without fertilizer given here. So the first thing I'll do is just discuss what type of test this is again. This is a one sample t-test because we are given one sample of data and a reference mean. Since this problem only asks if this fertilizer changes the pH and doesn't specify a direction, this is a two-tailed test. The null hypothesis is that the mean of our sample data is equal to the reference mean. The alternative is that the mean of our data does not equal the reference mean. Alpha will be given. Here, we'll use 0.05. Of course, this t-test can be performed in Excel, but we're going to go ahead and do it in R. When you first open R, that is RStudio, it should look something like this, and you may not have that fourth panel, which we need to write a script and save the script. To make a new script, go to File, New File, RScript, or you can click on this button here. Before we can work in R, though, we need to make our sample data. So let's go back to Excel, and we're going to copy the soil pH data. We're going to make a new Excel sheet with this data. And I'm going to paste it in this second row. I want to leave that first row open so I can label this data in a moment. Remember that R only likes data in columns. So I'm going to cut and paste each of these numbers into one column, making sure to paste them appropriately so they don't overlap and erase any of the data. Let's go ahead and name this data. I'm going to call it soil pH, being careful with the capitalization, which we'll see in just a second in R. I'm going to save this file, and I'm going to save it to my desktop for now. And I'm going to call it soil because that's the data we're working with. And this is very important. R only likes to work with CSV files. It will not work right with Excel files. So as this in the Save As type, I'm going to select CSV or comma delimited, or it may say comma separated values, and save this file as this file type. Be careful not to save it as the CSV Macintosh or MS-DOS or UTF-8. We just want regular CSV. We'll click Save. You may see a pop-up asking if you want to keep using this format. All this means is Excel is warning you that you're going to lose some formatting like the alignment or the borders or any colors you may have. And that's okay, that's what we want, so we hit yes. Now we're ready to load this data into R. Before we can do that though, we need to tell R where we saved our file. To do this, we'll go to Session, Set Working Directory, Choose Directory. I saved it to my desktop, and even though it doesn't appear here, I know I saved it there, and I'm going to open the desktop folder. And you should see output in the console, set WD, which stands for set working directory, to my desktop folder. To load data into R, we need to set it to a variable, hopefully a descriptive variable, just to help you keep track of what's going on in your script. So the variable I'll choose will be soil. To assign data to a variable, we use the arrow sign. And to read a CSV, we use read.csv. Open parentheses to start the function. My file was called soil.csv, and I could type that all in, and that would be fine, but then you have to be careful about the spelling and the capitalization. So remember, you can start typing it in and press tab, and it will automatically fill the rest of that file name, or it will give you a drop-down menu of the different files you can choose from. We need to tell R that this data has a column name, which is set by the header argument. So we'll say header equals true. It does have a column name. And now we will run this line using either the run button here, which you can click on, or pressing Control Enter on your keyboard. In the console, we see that R ran the command. It doesn't output any data yet because all it did was assign the data to a variable. The next thing you always want to look at is, what does the data look like in R? To do that, use the function head, all lowercase, and we'll input the variable name here. Again, being careful with spelling and capitalization. Sometimes it's easier to just copy and paste that variable so you don't have to worry about if the capitalization is correct. Let's run that line. And we see output down here. Soil pH is our column name, and then it starts in row 1 with all our numbers. The command head automatically outputs 6 lines of data. Now that we know our data looks correct, we are ready to run our one sample two-tailed t-test. I'm going to go ahead and write that on here. Run a one sample two-tailed t-test. To run a t-test, we use the t.test function. The first argument is what data we want R to use. We're going to use the soil data, and then we need to tell it what column to use. We're going to use the soil pH column. You can either type it in, you can click on this, or you can press tab. For a one sample t-test, we need to set the reference mean, or mu, with the mu argument. In this problem, mu was 6.3. This is all we need to run a one sample two-tailed t-test. So go ahead and run that command. Looking at the output, we see a one sample t-test was run on the soil data with the soil pH column. The t-value here is t-calc. It also tells us the degrees of freedom, 19, and the p-value for the t-test. It also tells you the alternative hypothesis, the 95% confidence interval, and the mean of our sample data. To compare t-calc, we need a t-crit. There are two ways to find t-crit. The first is using the t-table in your lab manual. Remember, for a two-tailed t-test, we need to divide alpha by 2 because this table is only for one-tailed tests. Alpha was 0.05, so we'll use alpha as 0.025. Our degrees of freedom was 19, so we find the value 2.093. Because this is a two-tailed test, we will also need the symmetrical t-crit value, which is negative 2.093. Let's go look how we can do that in Excel. I'll go back to this Excel template. And in the t-crit calculations cell, I will use the t.inv.2t function because this is a two-tailed test with 0.05 for the probability, or alpha, and degrees of freedom. R told us it was 19. You can also calculate it from the data here. and we also get 2.093. To find the symmetrical one, you need to use negative t.inv.2t and the same inputs, 0.05 and 19. Now that we have our two t-crit values and our t-calc value and our p-value, we can make our statistical and biological conclusions. T-calc is more extreme than our t-crit value of 2.093. This means that we reject the null hypothesis. I'm going to go ahead and type that in my R script using this annotation or notes with the hashtag symbol. All right, since t-calc is greater than t-crit, we reject the null hypothesis. We can also come to this conclusion using the p-value. The p-value is 0.004. That is less than our alpha of 0.05. So since the p-value is less than alpha, we reject the null hypothesis. You should always get the same conclusions from your t and your p values. That is your statistical conclusion. So what is the biological conclusion? For the biological conclusion, we should go back to our original hypotheses, which said that for the null, mu is equal to mu0. So the mean of this data is equal to the reference mean given. We are rejecting the null, which means that this is not true. I'm going to go back into R to write this down. I'll say since we reject the null hypothesis, we conclude that the soil pH is significantly different with versus without fertilizer. This sentence can be worded in many different ways, but remember, you can keep it very concise and still get your point across. The next thing we'll do is look at how we can use the t-test function with confidence intervals. So by default, the t.test function gives you the 95% confidence interval, which you can see down here. But if you wanted to get a 90% confidence interval, that's really easy to do. We just need to change one argument. So we'll use t.test. We'll use the same data, soil with soil pH, mu equals 6.3. To change the confidence interval level, we'll set the argument conf.level, and you can press tab or click on this one as well. And we'll set it to 0.90 for a 90% confidence interval. When we run that line, we can look straight down to the 90% confidence interval line, and we are given the lower bound and the upper bound. Next, we'll review how to change the t.test to run a one-tailed test. If you'd like to run a right-tailed t-test, in that your alternative is the sample mean is greater than the reference mean, we will use the same data, mu equals 6.3, and we will change the alternative argument to greater. Again, this is because our alternative hypothesis is the sample mean is greater than the reference mean. When you run this function, you'll get the same t-calc, degrees of freedom, but a different p-value. Finally, to run a t-test for a left-tailed t-test, we'll use t.test, soil pH, this time we'll set our alternative to less. Make sure every function has a closing parentheses to that open parentheses. When we run this, we get the same t-calc and degrees of freedom, but a different p-value. Your conclusions from your t-value and your p-value should be the same. And be sure you know how to draw a biological conclusion from your statistical conclusion. The last thing we'll look at here is how to save the R script so you can submit it during an exam. To save the R script, we'll go to File, Save, and I was working on my desktop, so I will also save my file on my desktop, and I'll just call it Soil Analysis. Don't change the file type, just click Save, and this file is what you will submit to Dropbox on Beachboard. This concludes the video on one sample t-test.